Calculation of CFSE in tetrahedral complexes. These are the degenerate orbitals, 5 d orbitals which are having the same energy. Those orbitals are dxy, dyz and dxz. dx square minus y square and dz square. So when they are having the same energy, we call it degenerate orbitals. When a ligand approaches these orbitals, they get an increased energy. Their energy increases and all of them will be having same energy. Then under the influence of that ligand, they split into two sets of orbitals, dxy, dyz and dxz, going to a higher level, that is the T2 set, and dx square minus y square and dz square coming to a lower level, that is the E set. So they split into two sets, T2 set and E set. In octahedral complexes, T2G was below and EG was up. Here we are avoiding the letter G because there is no overall symmetry. Now this line, dotted line in the center, is called the barycenter center. It is having a value of 0. The quantities above this 0 are considered positive and the ones below is negative. So these orbitals are associated with an energy. Each of them are having an energy of 2 by 5 delta T, increased energy of 2 by 5 of delta T equal to 0.4 delta T. And these orbitals dx square minus y square and dz square are associated with a decreased energy of minus 3 by 5 of delta T equal to minus 0.6 delta T. And the difference in energy between the T2 and E levels is called delta T, that is the crystal field splitting energy of tetrahedral complexes. Tetrahedral complexes is denoted by the letter T here. Now in the case of tetrahedral complexes, delta T is often less than P, where P is the pairing energy. Pairing energy means that energy required to pair up the electrons. An orbital having a single electron like this will be said to be paired if another electron comes in here. That is the capacity of an orbital, 2 electrons. So if there is already one more electron can be placed here. But in order to place the second electron here, you need a certain amount of energy. In these complexes, in these tetrahedral complexes, that pairing energy is high. So what do? If one electron is here, another one is here, instead of getting paired here, the third one will go up here because delta T is less than pairing energy. If pairing energy was less, they could have occupied this place only. But when the pairing energy is high, it is easier for those electrons to go to a higher level. So when pairing energy is high, no pairing takes place, there is no pairing. So in the calculation of this crystal field stabilization energy, we need not consider the pairing energy if the pairing energy is said to be high. Now let us look what's the formula for the calculation of crystal field stabilization energy is. That is for a tetrahedral complex. CFSE equals minus 0.6y plus 0.4x the whole into delta T. Since delta T is less than P, no need to add pairing energy. Then y is equal to, in this formula, y is equal to number of electrons in the E set and x equals number of electrons in the T2 set. So CFSE or crystal field stabilization energy equals minus 0.6y plus 0.4x the whole into delta T and no pairing energy is considered if the pairing energy is high. Now the relationship between delta T and delta O. Delta O is the crystal field splitting energy for octahedral complexes, and delta T is the crystal field splitting energy for tetrahedral complexes. Delta T is less than delta O. You know the reasons. In the case of delta T, the ligand is approaching interaxially. So the probability of head-on interaction with the unpaired electrons in the degenerate orbitals is less when compared to that of the octahedral complexes, because in the case of octahedral complexes, the orbitals are lying along the axis like this, and when a ligand is coming, it is also coming along the axis. So the interaction, the possibility or probability of interaction is greater here. Whereas in the case of tetrahedral complexes, the d orbital lobes are like this, and they are coming like this. So it may not be coming straight like this, it may be coming like this. So the probability of interaction is less in the case of tetrahedral complexes, and also more number of ligands in the case of octahedral complexes. In the case of tetrahedral complexes, there are only 4 ligands, whereas in the case of octahedral complexes, there are 6 ligands. So the number of electrons will be different, and so the repulsions will also be different, or the repulsions will be less in the case of tetrahedral complexes. So delta T is less than delta O, and delta T equals 4/9 of delta O, or delta T is equal to 0.44 of delta O.